Hello, everyone. Thank you for attending my talk. I'm going to give you an introductory view and information about how the internet works. I call it picking beneath the surface of the world of the internet. And I try to keep it simple. And actually, what I want to do is I want to start with going back to talking about how postal system works a little bit, and telegraph works and telephone works before I go to the internet. Okay, with that, let's look at what I have for that. So you want to communicate, that's what it is, I say, and let's start with the postal system. And interesting thing about postal system is that if you look at a postcard, not many of us do anymore, but it's still useful to understand how it works. Let's say you want to send a postcard to your grandma. So you write your note on the card on the left side and write her address on the right side. And then you drop it at the post office. So usually it goes from a post office or to a bigger post office, we call it sorter, and then goes to the next one, and so on, and some way finally arrives at the grandma's. So let's look at the postal system as a network. So I'll tell what a network means. So I have a local post office here. I got a picture of 4 cities in Assam: Guwahati, Nagaon, Jorhat, and Dibrugarh. And so I am dropping off my postcard at locally in the Guwahati post office, and then I want to send it to my grandmother who used to live in Dibrugarh, right? So what happened is that the local post office in Guwahati, the sorter, the main one, they will collect all the different postal messages, packets into one truck or whatever, take it to another. Depending on where the truck is going, it may go to, say, Nagaon, Nagaon to Jorhat, to Dibrugarh, or from Nagaon to Dibrugarh directly. That's why what you end up seeing is that you can say that you can go multiple different ways to send that postcard from one place to another. Me as a writing the postcard, I don't care how it got there, but I only wanted to make sure that it gets there. But from a postal network point of view, there's a network involved, like the way we're drawing it. So when I use the word network, it doesn't mean it's a TV channel, obviously, TV network. It means the network in terms of the representation of the locations on the that connects it. In this particular picture, what you are seeing is that I have 4, what you call is a node locations: Dibrugarh, Jorhat, Nagaon, and Guwahati. And they're connected by what we call is the links. So links and nodes, when they're connected together, form a graph or goes to a network. Okay, so graph is another term used for this purpose. And we usually like to call it a network when on a graph you actually carry traffic. In this case, the traffic being carried is the postal package and stuff like that. So far, so good. So keep that thought in mind. There's another important point to note. The way the postal system works, we call it actually a store and forward network. Why do we call it store and forward network? Because you have to store it in Guwahati. It may sit there for a day, then it go to Nagaon, sit there for a day before it sort them again, and eventually get to Dibrugarh. That's the idea of a store and forward network. So the message delivery in postal system works with that. Second thing about the message is that delivery is I already talked about the address is very important. It needs to know where it is going to be sent to. So let's look at a little bit of communication network history. So I talk about the postal network. Obviously, postal network is a form of communication. I'm now going to talk about electrical or electronics communication network and what we have been able to do it. The idea is to send a message quickly. Quickly means in a few seconds or a minute, you can actually get from one place to another, not like a postal system, which may take 3 or 4 days. So telegraphy is the first one, and in fact, first telegraph was sent in 1844 between Washington, D.C. and Baltimore. And I'll come back to about it in a little bit and talk about that later. Telephony, the first telephone call, that's another communication. That's not sending message, but that's the call. and that was 1876 was the call between Graham Bell and Thomas Watson. I didn't say when this was invented, I said when the first communication was started. And in the same way in internet, we say 1969 in the ARPANET, the first message was sent. So let's revisit telegraphy. It's a fascinating thing because it involves some of the ideas from telegraphy actually applies to internet. So telegraphy works on something called the Morse code to transmit between two stations. That's the point-to-point idea, okay? So each letter and a number has a code that's mapped up with, made up of dots and dashes. So each letter actually is going to be a combination of dots and dashes to make up the, or its number for that matter will be that like that, right? So here is an example on the side of the I showed it is the International Morse code. You can see the letter is A is represented by a dot and followed by a dash. B is represented by dash followed by 3 dots. So that's, you can see it. Very important thing to note here is that that the letter E has the least amount of the information needed to send it. It only has a dot, okay? And the letter T has a dash. So you might wonder why they did not put a dot for letter A, because that's the first letter in the alphabet. The reason is that if you look at the English language, the letter E appears the most if you look at the frequency of its appearance in any kind of text. And that's why you want to do minimum amount of work to transmit that most popular information. And that popularity idea is very important in encoding information. Even today, these days, we use it for file compression and whatnot, this sort of an ideas, right? And goes back to first being addressed with telegraphy, actually. So let's say if I want to send the message state for SOS in the Morse code, you can see that I have 3 dots. That's for the letter S. You can see it here. I circled it. And then followed by 3 dashes, which is the letter O. Letter O has 3 dashes. And then if you look at the letter S again, you get 3 dots again, right? So that makes it up. Now you have an interesting, what we call is a challenge. The challenge is here. Can you look at the number 3 here? What do you see in the number 3? It has 3 dots followed by 2 dashes. So if I transmit 3 dots followed by 2 dashes, how do you know it is not S followed by O, as opposed to the, maybe you are trying to communicate the number 3 first and followed by, something the number 6, which has a dash and of course 4 dots. I'm showing 3 dots. Maybe that's what you're trying to communicate. So this is where we need to have what is called a boundary or a delimiter between sending information. Only then we know what we are trying to communicate. And in the case of telegraphic, the boundary or delimiter is indicated by basically time. So what it says that because it is sent as an electrical signal, between symbols, dots and dashes of the same letter, 1 time unit is actually needed. Okay, so you're going to wait for that. And between letters, you wait for 3 time units. So it's a kind of almost think about like a second to make it easy to understand. So telegraph operators become extremely good at timing it well. So timing matters to be able to transmit it because we have to be able to delimit, distinguish between different letters and numbers when it's arrived at the other end. So we're going to send something. So although I showed the SOS message that dot, 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 dash, 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 dot, dot, dot. Remember, between symbols, dot and dashes of same letter, so you are going to do 1 unit of time. Between letters, you are going to add 3 units of time. So what I actually did is I did a dot, wait, dot, wait, dot, wait, 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 then dash, wait, dash, wait, dash, wait, 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 then dot, wait, dot, wait, dot, wait. So that's sort of how they have to transmit it. So the receiving side, based on the time spacing, can figure out that Yes, you are trying to send SOS, not something like you're going to send 3 followed by 6, right? Very important. So one other clarification here is that the time duration of a dash is 3 times the duration of a dot. So when I was speaking it out, I obviously didn't wait for a longer dash. The reason is that usually dot or dash, you send it as an electrical pulse. The electrical pulse takes on height. So if you go to height, you want to skip the electrical pulse for a longer time because you want to distinguish between dot and dashes. So we're going to wait basically 3 times duration. So timing up all of this is very important. And in a sense, telegraphy is the first protocol. And you'll hear the word protocol with the internet a lot. And this is one example of what you can actually get. Timing is very important. I talked about that already. What about address? Yes, you need to also have address. So each station is assigned a unique address, actually. And it's interestingly, in telegraphy, address is part of a message. So short addresses are preferred because then there's no conflict about it. A well-known telegraph address is, of course, Interpol, right? So you will do Interpol space and whatnot to follow your message. And if you notice that the code here, there is no code given for comma or period. What does it mean? That means you have to type out the word comma, C-O-M-M-Y-A, and period or full stop that you're going to type it up. So the receiving side then they can decode it based on that, and always the telegraph will actually have that entire word there. So in fact, there is an interesting manual on 1928 came out how to write telegram properly so they can save on time, space, and the money to transmit communication. So let's now do a quick comparison of postal network and telegraphy. Postal network is actually addressed person to person. We write it from one person to another, but telegraph was from address from station to station. So once it gets there, somebody has to deliver it to somebody, to actual person. Postal, you can write in any language because you're handwriting it, right? In the case of telegraphy, what happened when we went to the first electronic thing, we actually, in a sense, got limited. We could only use alphabets and numbers, but we couldn't use any other language. But what did we gain? We could deliver it in a short amount of time. Within a few minutes, can do it. And the other interesting thing, remember postal system I talked about store and forward. That store and forward is not necessary in the in a telegraphy. Now let's look at telephony. Telephony is again between any two persons. You also get an address. So address is actually, not for the person, but who it is, actually what location you have it, like your house or office, a telephone number, right? And again, suddenly language is no barrier. You can speak in any language. Your voice signal is transmitted. We have learned enough about electrical signals in the span of from 1844 to 1876 that we know how to convert from voice to electrical signal. And later it was digitized, what is called the pulse code modulation. The one very interesting thing is that each call gets a dedicated circuit or path, and that goes to a term we commonly use called circuit switching. Why this is important is that you remember what is store and forward. You can actually use the term then as a store and forward switching if you want to do it postal system. Postal system, you don't get a dedicated path. What do I mean by that? That means, remember I had a picture of the truck. So you're going to put a postal truck, you're going to put everybody's message together in one bag. You don't separate it out for each one as a separate thing and line it up on the truck, right? So it goes to as a one bag. But by looking at the address of the arriving point, then I can actually say, oh, this is for going to Naga or it's going to Dibrugarh. You can actually take care of that. So that's why it is actually very important to understand that distinction between dedicated versus the idea of shared path. Shared path means that we can put things together. And keep that thought in mind. I'll come back to that in a second. So the idea of the shared path, Leonard Kleinrock actually talk about something in the context of communication network, and that gave to the term called what we call is a packet switching. And so the packet switching, he said that it is viable option. He actually showed some work said that, used something called queuing theory actually to show that when you have a lot of packets to send together messages, it's actually better to do it that way. It's cheaper than having dedicated path like circuit switching. The other important historical tidbit is the Paul Barron's seminal paper that came out in 1964. He talked about what is called is that how can I think about an idea where you break an electronic message into smaller pieces? And his idea was that if we have a network, like the way I talked about, and send each of the small pieces in different ways, nobody in the middle, somebody sitting in Nagaon or Jorhat will know it because they don't see the entire message, they only see part of it. They cannot figure everything out. So Paul Barron was thinking that the military might be actually interested in that. That's the idea of breaking the message, not because of some other way to be able to do it. Obviously, once you break the message, you have to put it together when it gets to the destination. So this additional work can be done. So the question is it worth doing it, obviously, but it's a very important piece of work. So before I go further, let me now kind of capture the idea of circuit switching and go to the packet switching. Now, circuit switching, you can think about it. I think about like two lanes I have on a highway, and call 1 is going on lane number 1, call 2 is going on lane number 2. They cannot switch back and forth. They have to stay in their own lane. Packet switching idea is that the separation of the lane doesn't appear. That's why I put a dashed line in the middle. So so you can now think about idea of a packet is that packet can actually sort of like switching lane. They can mix it together. So here in an electronic system, so here I have a purple car that is switching back and forth like as you were driving on a road, right? And the black car is going another. They're mixing it together. When we mix it together, you have to now think about what we did with the postal system or what we have the telephone network. Telephone network, because you have a dedicated path, the idea of the address becomes very clear once you set it up, because you're not going to switch path. You're going to go destination and you got it. Nobody's mixing it up. Go to the postal system. When you put all the mail in one bag, unless you open it up, sort it through, and look at the address, you don't know who it is for. Until then, it is like in a bag. So packet switching is basically also looks like it is in a bag on this road or on a path or a link. But that means that only way I can separate it out, like is almost like the postal system. What you do is that you have to have an address assigned to each of this car. So here, I didn't assign an address, I just assign a color to distinguish them that, oh, this is the black one versus the purple one, right? So that's one way to distinguish. But if you can provide an address like the license plate in the front of the car, you can say, oh, this is who it is or who it is driving and whatnot. Same idea I can think about in applying it. So I talk about the Paul Barron's idea helps to send a large message, the first thing. That means if I have a kind of a narrow lane or narrow path or narrow link, I can actually send something and you don't have to do everything, you can break it down. So the packet idea or packet switching is actually coming to, and that's the term, as I say, Kleinrock actually used it. Then DARPANET Advanced Research Project Agency in US actually got involved. They did the initial funding in 67, 68, what is known as the ARPANET. And then an interesting piece, a very important piece of that did some initial work on it. And then Robert Kahn and Vinton Cerf in 1974 wrote a very phenomenal and seminal paper called a Protocol for Packet Network Intercommunication. And then now we call the word packet network with packet switching, instead of a postal network or telephone network, right? They define what is called a TCP or the transmission control protocol. That means how can we send packets or messages into the network by breaking into packets. And so they gave the name TCP, and that's its derivation is what we still use in the internet. It's a very phenomenal piece of work to get to that, right? And so ARPANET, a little bit of history. First node was in 1969. Second node was at SRI in October 1st, and that's usually said October is when the ARPANET was born because there was 2 points you can connect and start sending message. And third node was at UC Santa Barbara, I think, and fourth node at the University of Utah in 1969. 4 locations to connect the first ARPANET was formed. So now let's talk about sending a message. So you on the electronic network, let's say I want to send an email to grandma. So hopefully this animation works. So what you see, the blue colors are the routers in the network, correct? And then what happened, I broke the message into 3 parts or 3 packets. That's what I have. And they are going to be sending, theoretically it can send it through different paths in the network. That means through the different nodes I showed that. You can see the packet 1 is going through this node and going through here and to get there. Packet 2 is going this way, and packet 3 is going that way. And what happens is that if you actually kind of throw it out this idea of a packet different ways, like what Paul Barron's idea initially was, then what you do is that you have a situation, what is called that the packet 2 may arrive first, packet 3 may arrive next, and the packet 1 actually arrive last. So that means you have to reorder the packets before it is given to you. In fact, all your phone, the phone, I don't know if you can see my phone, I'm holding my phone, the phone, it is actually doing that all the time. Any web page you download, it is making sure that the packets are in the right order before it gives it to you, and very, very quickly. And the software takes care of it on your device, phone, mobile device, or laptop, or tablet, whatever you use it. The other point I want to make is that Paul Barron's point, which is basically say that if I am sitting in this location, that since only packet number 1 and 3 went through here, that location can never figure out what the message was because it's missing number, packet number 2. It can do partially, but it cannot decode it. That was originally idea about a packet network concept of distributed way of sending messages. On the other hand, the breaking into packet has a beauty of it because you can make big thing into smaller pieces. You can send it to the links in a network. They also have what we call it a capacity limit. We call the maximum transmission unit. So that we need to address it. So now let's take a look at what we need actually in a packet. So it is very clear we need to have a destination address. Packet needs to have a destination address. Think about like the car I talked about, the car license plate. You have a destination. It's like a license plate is saying that where it is going to go. That sort of think about like that. But on a communication network like internet, obviously, we need to also say what else it is for. Is it an email or a web? So I again give the analogy of cars. I love using analogy when I teach computer networks, and especially using the example of cars. What you see is that the way we can distinguish for a car is that the different cars, we know it. It's a truck, or it is a bus, or it is a small car. We know what it is. But on the internet, we have to be able to, since these are packets in an electronic form, sending with zeros and one, we need to be able to distinguish about where these things appear, differences appear. So you need a way to indicate in the packet, hey, I'm sending this packet. It is actually something different for, right? Another thing we found out by looking at that illustration I did, the animation I did, the packet number is important so that you can put the message together when you get to the end. Another thing is that you have to know is the packet number 1, 1. How does the destination know that this is the first packet? So you have to indicate another way to say that it's a start of a packet, start of a message, middle of a message, sort of an end of a message. So as long as we can capture those things, we can actually do it. So that means what happens, as opposed to postal network, in the case of communication network, along with the address, I need to have additional pieces of information, and that's what is known as a header of a packet. Only after that, you can have actual data. You can think about like a car, you have a driver, this is part of the header. Passengers are actually the data that's being transmitted, right? And so again, to recap it, each packet has a header and a data. And sometimes this data, the actual part of the data, we call it payload. The term actually comes from all the Apollo missions when they call it payload with sending the rockets to the moon. So how to communicate? Since two computers are talking to each other, by computer it could be a mobile phone or a server, doesn't matter. We need to have rules both sides agree. So remember I talked about telegraphy. So there was a protocol agreed in terms of letters, how each letter and number and whatnot. So in the case of the protocol for communications of today's communication network, you need not only that sort of, it is done slightly differently because we can distinguish between the spacing of time and how to encode, because we're in a digital world now from an analog world of signals. So we can actually first transform the zeros and, signals to, let me step it back. First, we can create zeros and one, then transmit it into analog form, and receiving side can actually at the high level, at a low level, they can change it from the analog signal to digital signal. But besides that, I can actually, now to this signal, we can actually put a boundary in certain ways to be able to do it. So for example, what should be in a packet? We know the header, what should follow in terms of rules. So the protocol also takes care of the rule, how both sides should agree in terms of communication, and what those routers need to do along the way, right? So let's here look at, I put to this thing. So a TCP, transmission control protocol, has a, what is first called, before you even send a message, you actually do what is called a handshake or connection setup. So I'm giving a very high level view. The client, that means me, I want to request something. I send a hello message first. Of course, you and I don't see it because it goes underneath. That's why I call, under the surface, what is going on the internet. Server gets it, says, oh, I got a new request here. Okay, I'm going to say yes, hello back to the other side. And the client then says, yes, got your hello, and responds back to the server. And this is called a three-way handshake. So every TCP connection, a protocol set us up to TCP, you have to have a three connection. Only after that, the real data is going to be done. These three connections are also packets. These packets are only communicating with some tricks in the header to say that I am a starting packet, hello packet, I am a response to the hello packet, and then whatnot, right? These three packets have no data in it, okay? No actual data, no payload. So remember, very important. So only after that you can start having again and this thing, whatnot. But there's a very important point when you look at this picture. The important point is that once the hello is received by this server, when it has to respond to it, so remember, it will be going to be like what? The postal message. Everything is going to be, all packets will be mixed up in an electronic communication link, right? So we have to distinguish it. So one thing server actually needs to know is what? It needs to know who to send it back to you. And this is where we separate it from a postal address. In the case of postal address, the from field, you don't have to always fill it up because you don't care. You can only need to do with the destination address, the to field. But in the communication network, because of this going back and forth, you need to actually, source has to also embed the source address. So the destination, when it reads it, they said, oh, this is the source address, I need to return it back. So what that means is the packet header has both the source and the destination address to identify it. So not only one address, and that's built as a part of the protocol. Good. So that's sort of what I captured in particular side here. So now if you look at the TCP handshake, it's kind of funny. We kind of make joke about it. We said that, hey, I would like to get a sugar packet. And it said, then the other said, hey, I heard that you asked for a sugar packet. Then I say it again, I did ask for a sugar packet. And then finally said, okay, here you're going to get the sugar. So essentially you have to do some amount of communication back and forth to get to that. This is a longer TCP joke, and I'll let you quickly look at it instead of me reading it. So, and the funny part is that there's also an idea called a connection timeout if you cannot get it. And so I'm sorry, your connection has timed out. Hello, would you like to hear a TCP joke? That means you're going to repeat the same thing again. So let's go there. The other important thing to note is that a packet can get lost. Even in the postal system, we know the card or something get lost. That's unfortunate. And then you have to tell the grandma that, some other way said, I'm going to read it. Grandma is waiting there that you're going to, send a card, and she didn't get a card. And when does she tell you that I didn't get your card? It's 7 days, 10 days, 2 months. So in the communication network, we also have to take care of what I call it the packet can be lost. The packet can get lost actually a couple of different ways. Remember I talked about the router? The router may not have enough buffer, enough capacity at that point to be able to store the packet, because a lot of packets are going through a router, right? And so you need to be able to think about like a traffic light with a road network. You know, you just said it can hold certain number of information at that point. So packet can get lost. So this cannot go there. Second thing is that during the time of transmission on a link, it may get corrupted. A letter 0 may become 1, 1 may become 0. Why? Because eventually, remember, even the digitized information is sent over as an analog signal on a cable, and the cable may have some hit on it, power hit or whatever, something get corrupted, you know. So the receiving side, when it gets signal, it moves it back from analog to digital. A 0 may become 1 or 1 may become 0. So a receiving router that has to actually do what it has to do may discard a packet because it says that it is not a good packet because it got corrupted during transmission. How does a router know it's not a good packet? It's called that the header, actually it is done in the TCP header, sorry, IP header. I'll come to IP in a second. IP packet header, and that says that it has to have something called a checksum operation that can basically look at the bits and all the bits of zeros and ones, and hey, this is a packet has an integrity in it, right? So then it's a good packet, and so and whatnot. So since we want the packet to eventually get to the destination, maybe it's your packet number 2, took a different route. The question is how long, I mean, you have to then decide what to do with it. It basically says that somebody has to tell that, hey, I didn't get the packet number 2. And the sender has to know that I need to retransmit the content of that packet as a sender. So let me illustrate again by this picture again. Let's see if it is going to work. Let's say packet number, going back to the example I had, the packet number 2 gets lost, right? Packet number 2 gets lost. What you will see is then is that somebody has to realize, in the case of the TCP, the Internet Protocol, the destination machine says that, hey, I got 1 and 3, I didn't get 2, because it waited for some time. Maybe it took a longer path to get there. You know, it's like you and your sister trying to visit your mother, go in 2 different cars, or your sister stops and buys something at a store, and she didn't get to the destination. Your mother asked, what happened to your sister? And he said, I don't know, I drove on a separate car, I got here, and we're waiting for the sister to come so that we can have dinner together, right? And she stopped. So in the case of, similarly, the receiving computer has to say that, said, hey, what happened to packet number 2? And then this is also why the source address is very important, of the source of the where I am trying to send it. And so then it sends basically another message saying that from this side, that it is going to send it to the other direction. So this is where I put where is packet number 2 is going to reverse direction. Goes to, that's where you can see that why the source address is important. And I get it. I said, oh, it didn't get to the computer my grandmother is using for checking email or the text message to nowadays. I got to resend it. So I'm going to resend this packet, and I'm going to send it. It may not take the same path to get there. So as I said, the source packet must always also have the source address, and eventually packet number 2 gets there. I reassemble them and give this thing. And sometimes you notice that because you're waiting, your page is not loading it up. It has a many different reasons. One of the reasons is that one of the packet is missing to get to you, is getting an your mobile device is requesting back to the server, so that send me packet number 2, and I'm going to do it. So in the context of the internet, it runs on what is called a TCP/IP protocol stack architecture. So let's kind of decipher its pieces to it. So first piece is that I talk about a little bit about actually only about transmission control protocol. I talk about packet, but in the case of TCP/IP, it is broken into 2 parts called TCP and the IP. Is the internet protocol. That is actually where the addresses are hiding for source address of the and destination of the devices. Very important, and that's assigned to that. Okay. And so, and then second word, you'll see that I use a protocol stack and architecture. What the heck, what does architecture mean? So let me give a different analogy. Let's think about the grocery store architecture. It is from I think it's from one of the computer networks book by Jim Caruso and Keith Ross, two people I know very well. And so they actually said that, think about like a grocery store. When I go to the grocery store, I pick up whatever. I'm a consumer, I pick it up. I pick up fruits, vegetables, anything else. And I just go there and get it. I don't care how the grocery store gets it. We know that grocery store gets from suppliers. Suppliers are not producers themselves. They got from the actual product source. It could be a factory that built it. And so it comes through there, right? So the beauty of this idea of dividing as an architecture, that's why you call the word architecture. And it's a different way of using the word architecture than your architecture for buildings that we talked about in the very commonly used, right? And so, that you can separate the functions. So this is sort of like what is the, another way to think about is the architecture is needed to do what is called a divide and conquer of trying to do something. And so it gives you flexibility and independence to do it. So in the case of TCP/IP architecture, TCP does certain thing about retransmission. IP's job is that, hey, I'm going to just drive. I don't care who is in the car, you know what it is. So you can divide that part and it allows you to address everything. So for internet world, now we have to add a little bit more thing. Remember, we have the application. We might have the web, the email, file transfer. So we need to allow the reliable transmission. That's called end-to-end routing in the network. That's the part is not reliable. Remember, I talked about packet getting lost, not lost because of corruption in the link, or there's no space in the buffer at a router. So that's unreliability part of it. The unreliability handle it end-to-end. And so very important. And last part is the Ethernet. So you can, this is where the idea application, because of the initial name of TCP/IP, we call it TCP/IP stack, but obviously there's an application that is built on top of that. So good, so we got to that part of it. Now I give you a broader view of this. Think about, we always draw, this is our view of architecture picture, right? So as if we're building something, right? We got a cable, Ethernet comes, Ethernet is like the Wi-Fi, your Wi-Fi uses Ethernet protocol, for example, that use it, that IP and the TCP and all the protocols. So even the application is a little bit of a interface. To be honest, we should call it application layer protocol, and we do call it, but I was not distinguishing it so far, just to make it simpler to understand what is going on there. So I kind of talked about that retransmission and all this stuff. So basic idea, and you know what's network job is, what the job of the transport protocol is. Very good. So yeah, we already split it up. I wanted to make a quick point going back to telephone network. The telephone network doesn't have the distinction between transport and the network layer. This is a new idea and thought process when the TCP/IP architecture was done, going back to the work that Bob Kahn and Vincerf actually did, right? What about IP address type? Now we're going to get to the car, real car part of it, right? The car is that you have to think about, and so address, so let's kind of revisit postal address for a second, and then we'll go from there to see what that means. So postal address, if you look at it, has three components broadly. What I call a user, the person's name, that means house address, postal street address, or the city. I call it city as a broad naming for city zip and the pin code. In US, we call it zip code. In India, it is called the pin code. You know, so every country has some kind of a code for the city and the post office and whatnot. So the best thing to think about it is from a computer network point of view, as if you organize the address in the reverse order. City is the least granular part, then the house or the street address, the user is the last one. You kind of break it up that way. So now what you can think about is that your web or the email is very close to the idea of a user, because that's like distinguishing who it is for or what application it is for. application at that level, protocol-wise, application layer protocol. Okay, the city and the house address is sort of like the IP address part of it and whatnot. Good. So you kind of, so essentially you can think about that TCP/IP has a two address part. One part is for the routing part for IP network. The other part is for the TCP part to say which application layer protocol I want to give it to. And so I want to point out the postman doesn't need to know who actually it is. As long as it drops it at the mailbox in my home, it doesn't care, you know, she doesn't care who it is for. And I get it and I give it to, you know, whoever is living in the house, that, oh, this is what you got and whatnot. All right. So that's important to understand that we actually divide and conquer the function also that way. So going back to the address, adding the pin code, if you look at in India, pin codes are 6-digit. You have 781014. Let's say that's where I'm sending it from. And going to my grandmother, 786001. If you know, in India, this number is also has a hierarchy from the left to right. So 7 actually represents a zone code. It's the eastern zone, I think, starting in West Bengal and whatnot. 78 is for Assam. 781 is for Guwahati and whatnot, and 014 is a particular post office. Similarly, 786 is for Dibrugarh, and 001 is for, you know, that particular post office in Dibrugarh. So that's important that we can actually distinguish that sort of address even at that. So this kind of goes to the, let me skip through that idea that that the address of IP address. IP address also has this sort of a breaking it down. Breaking it down, you know, you can think about it two different ways. So, you know, one is what is called the IP address, called a network address. Typically, is the first two part is the 32-bit address, is the network address, and last part is called the host address, or the last part of it. You can think about it. And I'm not going to talk about subnet mask today, but just kind of give you the idea about what it is and whatnot. So quickly, IP address is a version 4 address is 32 bits. 32 bits is that basically divided into 4 octet dotted decimal address. For human consumption, we write it like 170.16.21.33. So that's the address of your, that's your phone has it, and to be able to communicate, right? And so that's what it is. But I need to tell you one more thing is that the addresses can be basically two. Remember, I talked about the pin code. Pin code has a hierarchy from left to right because it tells you what it is indicating it that way. In a computer network, you always debate between that, whether it's a flat or hierarchical. If you look at the telephone number, it has a hierarchy. It has a country code like India +91, US is a +1. Then you have a next code, which is for city code like Guwahati has a 361, and whatnot, right? So, and so you actually hierarchically address, and has a beauty of it being able to address defined address. Mobile phones, not necessarily always clear how the address is. So we always said there's a address can be hierarchical flat. In the case of the IP network, one component of address is actually flat, which is the network address part of it, not the host address part of it. And at some point, I'm going to discuss that more in detail later, but I kind of touches base on that. So this sort of, I covered it already. So now let's quickly kind of cover it. The last part is that how does applications use TCP/IP? Consider web. Web is what is called the HTTP protocol, hypertext transfer protocol, and it actually transferred the files or images which are coded with called HTML, hypertext markup language. First thing is, do not confuse between HTML and HTTP. HTTP is the protocol that runs on top of TCP. HTML is actually the how it is encoded for, so that you know it's a image versus a text and whatnot. That distinction is also needed for that part. So again, to kind of now go back to what we talked about from the beginning, you have a HTML page. You break it up into small chunk, give it to TCP. TCP is going to give it to IP to transmit it. So now it's like a car. IP is going to route those packets. We sometimes use the word datagram with that. Then if it gets lost, you retransmit and whatnot, and eventually you see the packet. Okay, The last thing I want to talk about is the domain name. Domain name is very, very important. What is a domain name? Domain name is like something like a google.com, right? So how is that related to the IP address I talked about? So it is done using something called a domain name system. DNS translation function, it is done. And it's actually almost, it's like a table of information that is done. And so Google can be addressed to this IP address I showed it. But the important thing about this is that when you separate out the domain name for search from an IP address, you don't need to have a tight coupling between the domain name versus and the IP address. It can be, the mapping doesn't need to be static. It can change. It can change every minute, every second, or you may decide to keep it static for another year or so. That's the beauty of doing it. And why this is also helpful: if you move a server from one place to another, you may get a new IP address. You don't have to change your domain name. You have a domain name, you like it. Other question that commonly comes is, what's the difference between something like google.com versus www.google.com? From a domain name perspective, both are actually exactly the same. But many cases, most places, they use two different ways. They actually don't know what a user might type, whether they will type google.com or www.google.com. So they want that to be able to reach for the users to reach them. So they will do it that way. That's one thing. And secondly, because it's different names, I can use different IP address for each of them. I can send it to two different servers. That means you don't need to have one machine to serve a page or web page or information. That allows it to have what is called a cloud, and I'll talk about cloud and data center network in a future session about it, right? Very good. So quickly, I want to say that the packet can have a different names because remember I talk about the layer, and so because of that, so you have an application layer data HTML file, TCP puts a header, IP puts a header, and then Ethernet, your Wi-Fi puts a header, and as well as a trailer to, remember delimiter I talked about, you need to have a delimiter to do it. Trailers used to delimit packet Ethernet frames actually. And so eventually, just for your information, default TCP header is 20 bytes, IP header is 20 bytes, Ethernet is 14 bytes. You can now add those numbers to see that to send the data, the actual payload, you have to do this much of padding or header and trailer to take care of it. So I'm going to end with some trivia. So the trivia has to do with, let me see what I was going to do. Trivia has to do with, okay, so do with that first telegraphic message. It's very important. The Morse sent it from Supreme Court room in Washington, D.C. to his assistant Alfred Vail on May 24, 1844. He sent the message called "What Hath God Wrote." And it's a very important. Apparently, I think Morse's niece said that this is the first message you want to send. The second one is obviously the telephone call in 1876 between Alexander Graham Bell to his assistant Thomas Watson. He said, "Mr. Watson, come here, I want to see you." That's very, very famous with a telephone call. But what about the internet? What's the first message on the ARPANET going back to 1969? Actually, it was between UCLA and Stanford Research Institute. It sent two letters, letter L and O, then the system completely crashed. And they had to retransmit about an hour later. And what they actually try to do is that they are trying to connect between two computers. It is going to give you a login to be able to log in. So a failure doesn't mean it's a failure for a long time. We learn from failure. We all face failures in life, but it helps you to see what did not work, to learn something and create something new. And so with that, I'm going to stop it here. There are a few questions I got through the chat box. I'm going to quickly ask about it. First, one question is from Dipen Nath. He said, any chance of upgrade to TCP/IP architecture for the future? So that's a very good question. And at this point, there are some upgrades in certain ways. For example, IP address changing from IPv4 to v6 because we're running out a bit, more changes happening in the lower layer because of the transmission, whether you're going to transmit for Wi-Fi at the end as opposed to a core network, and the application layer new protocol. But overall architecture, I think, has a merit to it unless somebody come with it. The second question you had was the ISO OSI was an earlier version. It was actually standardized in the 80s. I still remember that. In fact, I first started learning when I took my computer networks course in, oh boy, 1985, I think. And so, and we learned it by OSI because TCP/IP was there. They thought TCP/IP was temporary. OSI was standardized. The problem was that OSI ISO stack was, it was so heavy. Implementation was challenging. TCP/IP was simpler. People are willing to implement it, and it became the de facto standard. Second question is from Pranjit. Pranjit said, can QUIC replace TCP? There's a new protocol called QUIC. Let me see if I can use this pen to write it. I'm not very good at writing. QUIC is actually, oh, I missed letter U here. The QUIC, QUIC protocol. This is actually proposed by Google. It runs over UDP transport, and it has a lot of benefit to it, takes care of a lot of security aspects, and those are the good thing. But it's still, I would say, quite limited in the sense compared to how prevalent TCP/IP is. Something that is legacy is not that easy to actually fully replace and whatnot. Another question is from Dana. Dana said that how do you visualize the future of the internet, the related system? That's a good question. I can see things, it is hard for me to see for applications. Apps like what we talked about. Now we got many different apps running over like HTTP protocol or their own version of the protocol created. And so anybody creating an app, if somebody is going to create a new Facebook or TikTok, that's hard for me to know. Somebody might create it in beneficial to a lot of people. On the other side of it, however, I can see that the future is the more from the core, because as we get into lots of data, we go to big data and to huge data, and we may come to a point where the idea of an application might be very different. You can think about more for telemedicine purpose and whatnot, and you want to have DNA data that you want to analyze over it. You want to do it very quickly. Maybe you submit the request, you may not see it, but you can actually do it from multiple different places. Data is located in multiple places. You can have a very interesting way to think about an application. That's not obviously common man's application in that sense, but it actually has a lot of potential there, whatnot. Let me look at a couple of more questions here. Tor is TOR is a very interesting thing, is that allows you to secretly send a message. I'm going to leave it there for now. And so let's see what else I got. And actually with that, I'm going to stop it here. Thank you for listening to it.